September 23, 1980. Langley, Virginia. Fluorescent lights hummed above desk after desk in the CIA's Soviet Analysis Division. Thomas Reeves, 42 years old, senior intelligence analyst with 16 years studying Soviet naval capabilities, squinted at the satellite photograph spread across his desk. His coffee had gone cold an hour ago. The image showed the Severodvinsk shipyard taken from 200 meters above Earth's surface. What caught his eye made him laugh out loud. His colleague, Patricia Hammond, looked up from her own stack of reconnaissance photos. Reeves shook his head and pushed the image toward her. The construction hall at Severodvinsk showed what appeared to be a submarine under construction. The dimensions were absurd. The vessel stretched nearly the length of 2 football fields. The beam width suggested something impossibly wide. Hammond studied the photo and returned it without comment. "Faulty lens," Reeves said, making a note to request recalibration. "Or they're building a decoy, trying to waste our analysis time." What Reeves didn't know was that within 3 years, his entire understanding of Soviet engineering capabilities would be shattered. The vessel under construction wasn't a camera error or a propaganda trick. Within 36 months, mockery would transform into something close to awe. The Soviet Union in 1980 existed in Western intelligence assessments as a technological also-ran. Yes, they had nuclear weapons. Yes, they had matched America's space achievements. But the sophisticated work, the precision engineering, the complex integrated systems that defined modern military hardware, these remained Western domains. The CIA had compiled decades of evidence supporting this conclusion. Soviet manufacturing relied on brute force approaches. Their aircraft were heavier than American equivalents because they couldn't achieve the same metallurgical precision. Their missiles required larger boosters because their guidance systems were less accurate. Their electronics lagged years behind Western semiconductor advances. Computer-aided design systems had revolutionized American engineering throughout the 1970s. Boeing designed the 767 almost entirely on CAD workstations. Lockheed used computer modeling for the F-117 stealth fighter. General Dynamics ran thousands of digital simulations before cutting a single piece of metal for submarine hulls. The Soviets had computers, certainly, but reports indicated they were massive, unreliable machines requiring constant maintenance. Nothing suggested they possessed the sophisticated CAD systems that had become indispensable to Western engineers. This technological gap shaped strategic assumptions at the highest levels. The Soviet Navy could build submarines, but they would be crude, noisy, and relatively simple. They could manufacture nuclear missiles, but the delivery systems would lack Western sophistication. They might achieve quantity, but never quality. These weren't prejudices. They were conclusions drawn from hard intelligence, defector testimonies, and decades of technical analysis. When Reeves saw those satellite images of the Severodvinsk construction hall, his laughter came from professional confidence. The dimensions suggested a submarine displacing perhaps 60,000 tons submerged. Impossible. No one could design something that complex without advanced computer systems. The hydrodynamic calculations alone would require millions of computational operations. The structural engineering would demand finite element analysis that only computers could handle. The systems integration for a vessel that size would need digital modeling to prevent catastrophic design conflicts. The Soviets simply didn't have those capabilities. The irony was that 5,000 miles away in a design bureau in Leningrad, engineers were proving every one of these assumptions wrong. Sergei Kovalyov, 53 years old, chief designer at the Rubin Design Bureau for Marine Engineering, sat at a drafting table that had seen 30 years of use. The tools surrounding him would have been familiar to naval architects from the 1940s. Mechanical pencils, slide rules, French curves, compasses, protractors, sheets of vellum stretching across the angled surface. Behind him, rows of identical drafting tables filled the Bureau's main design hall. 200 engineers worked in near silence, interrupted only by the scratch of pencils, the rustle of paper, and occasional quiet consultations. No computer terminals, no cathode ray displays, no digital plotters, just human minds, mathematical training, and patient, meticulous hand calculations. Kovalyov had received the project assignment in 1976. Project 941, Akula, later designated Typhoon by NATO. The requirements seemed designed to be impossible. The Soviet Navy wanted a ballistic missile submarine capable of breaking through Arctic ice to launch. It needed to carry 20 R-39 RIF missiles, each standing 40 stories tall and weighing 90 tons. The missiles themselves were enormous because Soviet solid fuel technology lagged behind American equivalents. This meant the submarine needed to be enormous to carry them, but size created exponential engineering challenges. Pressure hull strength didn't scale linearly. A vessel twice as large wasn't twice as difficult to design. It was perhaps 8 times as difficult. The structural loads, the hydrodynamic forces, the weight distribution, the systems integration, every element became vastly more complex. And Kovalyov needed to solve these problems using methods that Western engineers would have considered obsolete. "We don't have computers," his deputy, Anatoly Shvenchenko, had said during the first design review. "So we'll have to be smarter than the Americans." The statement wasn't bravado, it was operational reality. The team couldn't rely on software to catch errors or run simulations. Every calculation needed to be performed by hand, checked by a second engineer, then verified by a third. Every design decision needed to be thought through completely before committing to paper. Mistakes were expensive in time and resources. The methodology was painstaking. For the pressure hull calculations alone, teams of engineers spent 6 months running structural analysis, using nothing but slide rules, reference tables, and theoretical formulas. They calculated stress loads at hundreds of points along the hull. They modeled how the structure would respond to depth pressure, temperature variations, and combat damage. They determined welding requirements, frame spacing, and reinforcement patterns. All by hand, all checked and rechecked. The work proceeded slowly, but it proceeded correctly. Kovalyov made a decision that Western intelligence would later identify as either brilliant or insane. Instead of a single massive pressure hull, he designed 2 separate hulls mounted side by side. Each hull would be cylindrical, relatively simple to manufacture. Between them, the missile silos would be housed. The control room would sit above both hulls in a separate pressure section. This multi-hull design solved several problems simultaneously. Manufacturing 2 smaller pressure hulls was easier than fabricating 1 enormous hull. The side-by-side arrangement provided redundancy. Damage to one hull wouldn't necessarily sink the vessel. The layout created space for the massive R-39 missiles without requiring impossible internal engineering. But the design also created new challenges. The 2 hulls needed to move through water as a single unit. The hydrodynamic forces would be unlike anything previously calculated. The structural connections between hulls had to handle enormous stresses while maintaining pressure integrity. The ballast systems needed to keep the asymmetric design balanced. Every one of these challenges needed to be solved using manual calculations. Viktor Mikohev, 28 years old, junior engineer assigned to hydrodynamics, later recalled the process. "We built a wooden scale model 1/20th actual size. We took it to the test tank and watched how water flowed around it. Then we went back to our desks and calculated why the flow behaved that way. Then we modified the model and tested again. Western engineers ran digital simulations and got answers in hours. We spent months in iteration. But when we finished, we understood every aspect of how this vessel would move through water. We didn't trust a computer output, we knew." Construction began at Severodvinsk in 1977. The Severodvinsk shipyard, located on the White Sea near Archangel, had built Soviet submarines since the 1940s. The facility had experience with large vessels, but nothing approaching Project 941. The construction hall needed to be expanded. New cranes were installed capable of lifting sections weighing hundreds of tons. Specialized welding equipment was fabricated. Workforce training took months. The first hull sections emerged from the fabrication shops in early 1978. Each piece had been cut and formed according to blueprints prepared entirely by hand. The welders worked from drawings showing every seam, every penetration, every reinforcement. No computer-generated fabrication instructions, no automated cutting systems, human expertise guiding every step. The hull sections came together slowly. Each weld needed to meet exacting standards. Pressure hull integrity allowed no margin for error. At test depth, the external pressure would reach 500 imps per square inch. Any weakness would implode catastrophically. Quality control inspectors verified every weld using X-ray equipment. Failed welds were cut out and redone. The process was slow, expensive, and absolutely necessary. By late 1979, the first pressure hull was taking shape. The second hull began assembly 6 months later. The missile section between them started fabrication in early 1980. The sheer scale of the construction became apparent. The completed vessel would measure 175 miller long, 50-74 foot, nearly twice the length of a football field, including end zones. The beam width would reach 23 miller, 75 foot across. Submerged displacement would hit 48,000 tons, exceeding any previous submarine by 20,000 tons. The sail, the conning tower, would rise as tall as a 5-story building. The missile tubes would penetrate through the space between the hulls, each tube designed to house one R-39 missile, standing 16 millers tall. What Reeves and his CIA colleagues couldn't have imagined was the scope of what traditional engineering methods could achieve, given sufficient expertise and patience. The Typhoon's interior arrangement included features that computer modeling should have been necessary to optimize. The crew quarters were designed for 160 personnel. Unlike cramped Western submarines, where sailors hot-bunked and lived in conditions barely above prison standards, the Typhoon included private cabins, a gymnasium, a sauna, and a small swimming pool. These weren't propaganda additions. They were practical necessities. The submarine would patrol under Arctic ice for 4 months at a time. Crew morale and mental health required attention. Kovalyov's designers had calculated the space requirements, the weight distribution, the ventilation needs, and the resource consumption for these amenities, using nothing but experience and mathematical formulas. The nuclear reactors posed their own engineering challenges. 2 OK-650 pressurized water reactors, each generating 190 megawatts, provided propulsion power. The reactors needed to be positioned for optimal weight distribution while maintaining separation for safety. The steam systems, cooling systems, and shielding all required precise engineering. The calculations for reactor placement involved thousands of variables: weight, center of gravity, radiation protection, maintenance access, piping runs, electrical routing, and emergency systems, all resolved through manual engineering analysis. By mid-1981, the first Typhoon, designated TK-28, was nearing completion. The vessel had cost the Soviet Union roughly 1 billion rubles, about $1.5 billion in equivalent Western currency. The construction had consumed 75,000 tons of steel, 2,000 tons of copper, hundreds of tons of specialized alloys, and the labor of thousands of workers over 4 years. And still, Western intelligence didn't fully believe it existed. September 1981, the USS Augusta, a Los Angeles-class attack submarine, conducted surveillance operations in the Barents Sea. Commander James Patterson, 40 years old, 16 years in submarines, had received a classified briefing before deployment. Intelligence suggested the Soviets might be launching a new ballistic missile submarine. His orders were simple: find it, photograph it, record its acoustic signature, and stay undetected. The Augusta carried the most sophisticated sonar systems in the American inventory. Passive arrays could detect submarines at extreme ranges. Active sonar could map contacts with precision. Computer systems processed acoustic data in real time, filtering ocean noise and highlighting potential targets. Patterson was reviewing patrol reports when his sonar operator called him to the sonar room. Senior Chief Marcus Webb, 51 years old, had 28 years' experience in submarine sonar. He was listening to something on his headphones, his expression puzzled. "Commander, you need to hear this," Webb said, handing over a headset. Patterson listened. Through the electronic processing, he heard a low-frequency rumble, machinery noise, propeller cavitation. A submarine, definitely, but the signature was wrong. Too much noise from too many sources. The acoustic pattern suggested something enormous. "Bearing?" Patterson asked. Webb gave him the coordinates. Range. Webb consulted his displays. "Approximately 40,000 yards, sir, and he's not trying to hide." The contact was heading northeast at perhaps 12 knots. Patterson ordered a course to close the range while maintaining stealth. Over the next hour, the Augusta maneuvered into position. The sonar picture became clearer. The contact was a submarine, but the size estimation kept increasing. Computer analysis suggested a displacement around 45,000 tons. Patterson didn't believe it. No submarine displaced 45,000 tons. The American Ohio-class boats, the largest in the U.S. fleet, displaced 18,000 tons. A Soviet boat 3 times that size was absurd. But the sonar didn't lie. The acoustic signature showed 2 separate propellers, each driven by a dedicated steam turbine. The blade count, rotation rate, and cavitation patterns all indicated massive propulsion systems. Patterson brought the Augusta closer to within 20,000 yards. He raised the periscope briefly during a moment when the Soviet boat was turning, giving him a profile view. What he saw through the optics made him call his executive officer to confirm he wasn't hallucinating. The submarine sail towered above the water like a building. The hull width seemed impossible. The sheer scale dwarfed anything Patterson had seen in 16 years of submarine operations. He took photographs. He recorded the acoustic signature. He tracked the contact for 6 hours until it submerged beneath the polar ice cap where the Augusta couldn't safely follow. Then he turned south to report what he'd found. The report reached the Office of Naval Intelligence within 24 hours. Analysts examined the photographs and acoustic data with the same disbelief Patterson had felt. They ran the numbers again. Displacement minimum 45,000 tons, possibly higher. Length approximately 170 millers. Beam 23 millers. The measurements confirmed what the CIA satellite photos had shown. The Soviets had built the largest submarine in history, but intelligence assessments still questioned the technological capability. A vessel that size should have been impossible to design without computer-aided engineering. The structural calculations, the hydrodynamic modeling, the systems integration. How had they solved these problems? October 1983, the TK-28 completed sea trials and was formally commissioned into the Soviet Northern Fleet. By then, a second Typhoon, TK-22, was in advanced construction. The CIA obtained more satellite imagery. The photos showed both submarines at Severodvinsk. Additional construction halls were expanding. Intelligence estimates suggested the Soviets planned to build at least 6 Typhoons, possibly more. Defense Department analysts struggled to understand the strategic implications. Each Typhoon carried 20 R-39 missiles. Each R-39 carried 10 multiple independently targetable re-entry vehicles, 10 separate warheads. Each warhead had a yield of 100 kilotons, 5 times the Hiroshima bomb. A single Typhoon therefore carried 200 nuclear warheads. 6 Typhoons meant 1,200 warheads, enough to destroy every major American city simultaneously. And these vessels could launch from under Arctic ice, where American attack submarines couldn't easily pursue them. Admiral Hyman Rickover, father of the American nuclear submarine program, reviewed the intelligence reports with growing concern. At 83 years old, after 4 decades shaping U.S. submarine development, he understood what the Typhoons represented. The Soviets had achieved through traditional engineering what Americans assumed required advanced technology. They had compensated for lack of computers with superior theoretical knowledge and painstaking manual calculations. Rickover later told a congressional committee, "We became dependent on tools. They remained dependent on brains." Both approaches work, but theirs required more discipline. The truth slowly emerged through multiple intelligence sources. Defectors from Soviet design bureaus provided details of the engineering process. Satellite photography showed the absence of computer facilities at Rubin Design Bureau. Technical analysis of Soviet submarine components revealed manufacturing methods that relied on human precision rather than computerized machining. The picture became clear. The Typhoons had been designed entirely by hand. 200 engineers at drafting tables had performed millions of calculations. They had used slide rules, mechanical calculators, and reference tables. They had built physical models and tested them in tanks. They had drawn every line of every blueprint manually. And they had created the largest, most powerful ballistic missile submarine ever built. What they couldn't have imagined was how this revelation would change Western assessment of Soviet capabilities. The CIA had underestimated Soviet theoretical engineering knowledge. The Pentagon had overestimated the importance of advanced tools versus fundamental expertise. The intelligence community had confused technological sophistication with engineering competence. The Soviets had fewer tools but deeper understanding. Their engineers couldn't run thousands of digital simulations, so they needed to understand the underlying physics well enough to minimize errors. They couldn't rely on software to check their work, so they developed rigorous manual verification processes. They couldn't iterate quickly through computer-aided design changes, so they thought through problems completely before committing to solutions. Between 1981 and 1989, the Sevmash shipyard completed 6 Typhoon-class submarines: TK-28 Dmitry Donskoy, TK-22, TK-12, TK-13, TK-17, and TK-20. Each vessel cost approximately 1 billion rubles. Each required 4 years of construction. Each represented the culmination of hundreds of thousands of hours of manual engineering work. The submarines deployed to the Northern Fleet, conducting deterrent patrols under Arctic ice throughout the late Cold War period. They were based at Nurpacha, a facility built specifically to accommodate their enormous size. The service record of the Typhoon class validated the engineering that created them. Despite being designed without computers, they proved reliable. The complex multi-hull design performed as calculated. The hydrodynamics were accurate. The structural integrity held. The system's integration worked. Human engineering had achieved what Western experts thought required digital assistance. The submarines were not without limitations. The enormous size made them expensive to operate. The crew of 160 was large by submarine standards. The acoustic signature, while reduced by Soviet standards, remained detectable by American sonar systems. The R-39 missiles, though powerful, had ranges shorter than American equivalents. But these were design trade-offs, not engineering failures. Kovalyov's team had created exactly what the Soviet Navy requested, using only the tools available to them. Colonel Mikhail Petrov, naval attaché, who defected to the West in 1985, provided insights into the Soviet engineering culture that produced the Typhoons. Western engineers trusted their computers, he explained during debriefing. They input parameters and accepted the output. Soviet engineers trusted only mathematics and physics. They calculated everything from first principles. This took more time, but produced engineers who deeply understood what they were designing. When something went wrong, they knew why. They could solve problems in their heads that Americans needed computers to analyze. The design philosophy extended beyond submarines. Soviet aircraft, missiles, and spacecraft all reflected similar approaches. Fewer electronic systems meant more reliance on mechanical engineering. Less automation required more operator skill. Simpler computers demanded better software efficiency. These weren't weaknesses. They were different methodological choices that produced effective results through alternative paths. The Tupolev Tu-16 bomber, designed in the same era as the Typhoon, used similar manual engineering methods. The Energia rocket system relied on hand calculations for structural design. The MiG-29 fighter aerodynamics were optimized through wind tunnel testing rather than computational fluid dynamics. In each case, Soviet engineers achieved performance comparable to Western systems despite lacking equivalent design tools. The Cold War's end changed the Typhoon program's trajectory. The enormous operating cost became unsustainable for the collapsing Soviet economy. By 1991, all 6 submarines were still in service, but maintenance schedules were slipping. The Russian Navy inherited the fleet, but lacked resources to operate it. Between 1996 and 2002, 5 of the 6 Typhoons were decommissioned. The vessels were simply too expensive to maintain during Russia's economic crisis. Only TK-28 Dmitry Donskoy remained in service, converted to a test platform for new missile systems. As of 2025, this last Typhoon still operates occasionally, now 42 years old, a testament to the engineering that created it. Thomas Reeves retired from the CIA in 1994. In a 2002 interview, he reflected on the Typhoon program. We laughed at those first satellite photos. We thought they were making mistakes or building mock-ups. We were the ones making mistakes. We assumed advanced tools meant advanced engineering. The Soviets proved that deep knowledge and discipline methodology could achieve what we thought required computer assistance. It was humbling. Patricia Hammond, who worked alongside Reeves analyzing Soviet capabilities, wrote in her memoir that the Typhoon revelation forced a complete reassessment of how we evaluated foreign military technology. We had confused means with capability. The Soviets used different means, but achieved significant capability. The engineering methodology that produced the Typhoons has largely disappeared. Modern submarine design is unimaginable without computer-aided systems. The Chinese Type 094, American Columbia-class, British Dreadnought, and Russian Borei-class submarines are all designed using sophisticated CAD software, finite element analysis, computational fluid dynamics, and digital simulation. No major naval vessel has been designed primarily by hand in 30 years. The tools are too powerful and the advantages too significant. But the Typhoon era proved that such tools, while valuable, aren't absolutely necessary given sufficient expertise and patience. Sergei Kovalyov died in 2011 at age 84. His obituary in Russian naval publications praised his leadership of the Typhoon program. Western naval architects acknowledged his achievement. The American Society of Naval Engineers published a retrospective examining how the Typhoons were designed without computers. The conclusion was that Kovalyov's team possessed exceptional theoretical knowledge, rigorous quality control, and methodological discipline. They succeeded through excellence in fundamentals rather than advanced tooling. The lesson wasn't that computers are unnecessary. Modern engineering clearly benefits from digital tools. The lesson was that tools amplify capability but don't create it. Engineering excellence begins with deep understanding of physics, mathematics, and materials. Tools help implement that understanding more quickly and with greater complexity, but they don't substitute for knowledge. September 2022, the Dmitry Donskoy conducted trials of the new Bulava ballistic missile system. The submarine, now 41 years old, operated off the Kamchatka Peninsula. Russian Navy observers noted the vessel's reliability. After 4 decades, the basic engineering remained sound. The pressure hulls maintained integrity. The multi-hull design functioned as originally calculated. The systems, while updated over the years, worked within the framework established by Kovalyov's manual designs. The submarine that Reeves couldn't believe in 1980 had outlasted the Soviet Union itself, validated by decades of operational service. The irony was complete. Western intelligence agencies had dismissed the possibility of Soviet engineering achievement without advanced computers. They had underestimated the capability of traditional methods applied with expertise. The Typhoons proved that engineering excellence transcended the tools used to implement it. What Reeves didn't know in 1980, studying those satellite photographs with dismissive confidence, was that human ingenuity expressed through slide rules and drafting tables could match human ingenuity expressed through computer terminals. The Soviets hadn't found a way around technological limitations. They had demonstrated that such limitations mattered less than Western assumptions suggested. Within 3 years, mockery had transformed into recognition. Within a decade, dismissal had become respect. The largest submarines ever built, designed entirely without computers, taught the CIA and Western intelligence a lesson about the difference between tools and talent. Both matter, but assuming one requires the other leads to underestimating those who excel at fundamentals.